This is the video on the phases of matter and phase changes. So remember, in all of these videos, there will be codes. There will be two codes. One will be a written code on the screen. The other code will be a verbal code said by myself. Each code will be 3 numbers, and you're going to need those numbers in order to move on with the homework assignment. So when you're looking at these slides or you're looking at these videos, write what is in green. Put that information in your notebook. That just basically highlights the important topics. The rest of it is just good information, so it reads like concise ideas. So this is the written code for this video. I would recommend you write this down somewhere. All right, so let's just jump right into it. So solids. These are the attributes of a solid. They have a definite shape and definite volume. They do not take the shape of their container. It's the most dense phase, and the exception is water. Organized, difficult to compress. They're rigid. There are such things as amorphous solids. We don't really need to get into that too much, but you can see here that on this little graphic, you zoom in on a solid like a popsicle stick. You can see that has a definite shape, volume, and the those molecules or those atoms are the closest together. They're organized, they're rigid, they stay in the same place. Now liquids, these are the attributes to a liquid. They have a definite volume but no definite shape. They do take the shape of their container, a little less organized, so now the particles can slide past each other. They're difficult to compress. So if you zoom in, you can see here that you pour it into a container, it takes the shape of that container. Now you zoom in, those particles are less dense. They're moving around, they're past each other. Now gases, that third state of matter. These are the attributes of a gas, no definite volume and no definite shape. They do take the shape of their container, least dense phase. They will expand to fill a container. The particles are going to be bumping into each other, and they are able to be compressed. So vapor is a gaseous state of something that is normally liquid, so like water vapor. So if you zoom in, you can see here that it does fill the container. It takes the shape of the container. And if you zoom in, well, those particles, it's the least dense phase. They're farther apart. They're bouncing off of each other. Now, how do we get from to different of these phases of matter? It all has to do with energy. Energy is the capacity to do work or produce heat. Now, there are many types of energy, but in this one, we're going to be concerned with like the thermal, the heat energy. If you add energy to something, those particles move faster and matter expands. If you remove energy, particles move slower and matter contracts. They get closer together. That's how we go from different phases. So you can see here I go from solid, I add energy, this arrow up top, that heat energy, it's going to melt into a liquid. You add more energy, it's going to vaporize, become a gas. On the other side, if I remove energy, like I put it in the freezer, well, that gas, it's going to condense, become a liquid. That liquid will freeze and become a solid. Now, there are two phase changes that you don't really hear about too much. There are certain conditions where you can go directly from a solid to a gas or directly from a gas to a solid. So if you go from a solid to a gas, it's called sublimation. Now, this is like if you have dry ice. That's frozen carbon dioxide. At 1 atmosphere, it's going to just go directly to a gas. And going gas directly to a solid, that's a deposition. So that's a little harder. That's like if you put a penny on the dry ice, well, that copper is going to become really cold, and that carbon dioxide gas is going to freeze around the penny. That's deposition because it goes directly from a gas to a solid. So this is the phase change diagram that you should definitely have access to. Just has all the phase changes, all 6 phase changes that we're going to be talking about. Now, we said adding heat energy or taking heat energy away. There are certain words for that. It's called endothermic and exothermic. So endothermic change, heat energy is being absorbed or entered. So if I put an ice cube out, it's going to melt, and that's because the heat from the surrounding area is moving in towards the ice cube, right? And it's entering. It's an endothermic change. Now, an exothermic change, heat energy is being released or it exits. So the example that I use is that if I put a cup of ice water out on the table, well, what's happening is that water vapor in the air has a lot of energy, and it comes into contact with that colder surface, and that colder surface it takes that energy away. It exits that water vapor, and it condenses on the outside of the glass. So we've been using some terms, temperature and heat. Now, in real life, they've been used interchangeably, but in chemistry and physics, they have a certain meaning. So temperature is a measure of the average kinetic energy of particles. Objects do contain temperature. So this water has a temperature of this. You have a temperature of this. Temperature is just the motion of particles, the average kinetic. That's what a thermometer measures. It's basically a speedometer for those particles. Now, heat is a type of energy that is transferred between substances. Objects do not contain heat. Heat is just the transfer of energy. Heat naturally always flows from hot to cold objects. Now, heat and temperature are not the same thing. So let's do a thought experiment to reinforce this idea. So let's look at an oven, right? You're heating an oven at 400 degrees to cook a pizza. After the oven is done preheating and the pizza is cooked, well, what's the temperature of the air in the oven? It's going to be 400 degrees. Now, what is the temperature of the metal rack in the oven? Well, it's going to be 400 degrees, right? They both have the same temperature. Both were heated to 400 degrees during the process of preheating and cooking this pizza. Now, ask yourself, what would hurt worse? Feeling the air in the oven with your hand or grabbing the metal rack? Right, so you've probably done that. You've pulled the oven out, you stick your face in there and go, oh, is it done? And then hot air hits your face and you take a step back and go, whoa, that was a little too hot, right? But you're not like burned, right? You don't have to go to the hospital. You don't have third-degree burns. But if you stuck your hand and you grabbed that metal rack, then you would, right? Now, grabbing the metal rack would hurt worse because it transfers the heat to your hand faster than the air, right? So it's same temperature, right? They're at the same temperature, but that metal rack is transferring that energy a lot faster to your hand. That's why you get burned with that, but the air, not really. You just take a step back. Now let's look at another example, right? Standing in cold air or jump into cold water, even if they're at the same temperature. So we've all probably been doing this. You've been sitting and you're like, oh, I gotta take the trash out real fast. It's January, December, or it's just winter, right? And you have to uh, run outside real fast, throw the trash away, even though you're in shorts. You're going to be fine for that 5, 10, 15 minutes. You'll be fine. You can walk around. You're good. You're in no danger of going like, hypothermic, right, in that time. But if you were to fall into water at the same temperature, then yes, that would be a danger. And it doesn't have to do with the temperature, right? Both the air and the water would be at the same temperature, but what happens is that water can take that heat away from your body a lot faster than the air. That's why you can be outside in the cold temperature for, 5, 10 minutes, be perfectly fine, go back inside, and you wouldn't even think anything of it. But if you fell in the water for 5, 10 minutes at the same temperature, I mean, you would go hypothermic. You'd have to go to the hospital. And that's because, well, the water is taking that heat energy away from you faster. So these are the phase change diagrams that you're going to need to know. Now, this first one over here, this one's just saying, hey, I add heat. What are the different phase changes? Now, this one on the right is my temperature versus heat graph. So like I said, temperature and heat are the same thing. I can add energy, but watch what happens, right? Solid is going to be warming up, and then it reaches a melting point. It takes heat energy to phase change, to change phases, right? And that's what this is. It melts, I add more heat, and then eventually it all becomes a liquid. Then the liquid warms up and and then it starts to boil, right? So it takes that heat energy, even though it's going to be at the same temperature, it just takes energy to vaporize that liquid and then become a gas. Or if I go the other way, I take gas and I'm taking that heat energy away, it's going to cool down and it's going to condense. I have to take more energy away for it to become a liquid, and then it's going to reach that freezing point, and then it's more energy needs to be taken away before it becomes a solid, then it cools down. So it does take that heat energy to do a phase change. So we did do a phase change activity where you had to identify all of this, and at this time I'll go ahead and give you the verbal code. The verbal code is 473. I say that again, the verbal code is 473. And the lab that we did this week was called a Watch Pot Never Boils. So in this lab, you can see in the thumbnail, what we did is we took ice water and we put it on a hot plate, right? And we took a temperature every 30 seconds. We took the temperature every 30 seconds, and we could create a nice, it should look like the phase change diagram. And that's how we looked at phase change, heat, and temperature. So once again, there's just too much unknown in the universe to take a break from learning. Get out there and question everything.